today. So our new business today, we're going today to cover our last session for photogrammetry. That's the last session. And then on Thursday, we have our midterm exam. Then following the midterm exam, we will look at a different chapter, which is laser scanner. Okay. So let's get started here. And I have a little agenda for us. We have to cover something called flight mission planning, and which is not really brand new. So we talked about that our photogrammetry involves three stages. First stage includes planning step. So we will talk about planning step one more time. And we will talk about a very, very interesting topic in photogrammetry, a system that uses photogrammetry to create maps very fast, something called mobile mapping systems. We'll also look at their applications. And then our last part after the break, we will talk about satellite photogrammetry and some technical terms, and then we will look at the application of the satellite systems. Now let's get started here. So my first topic to cover is flight mission planning. You guys know by now, and that's not really a secret, anything you want to do, it needs some sort of planning. Planning will save your time, will save your money. I can tell you, we apply the same thing in photogrammetry. Photogrammetry, it's an amazing tool, but it has also some constraint. For example, I cannot fly my drone at night, not only because the regulation said no, but also if you fly your drone at night, there is not enough light and your photos will be just black, dark. So it means it's not going to help me in photogrammetry. So we have a very limited window for flying our drone in a day. So it has to be in a day. Also, we need to avoid early morning and late afternoon because those, they have maximum shadows. And we said in our class that photogrammetry doesn't like shadow. It doesn't work very well in shadow. So you must have enough light with minimum shadow. Also, when you look at the season, so if the ground is covered with snow, I'm asking you guys, I need some help. If the ground is covered with the snow, can I still use photogrammetry to create a 3D model?
No.
No, you cannot. And if you cannot remember that, please remember when we process the mask and the mask has had a white background. Whenever you have a white background that has no features for the software to detect or even for the human to measure, it means photogrammetry will simply fail. So you can see here, we have kind of limited, we're constrained by so many constraints. Probably I can tell you two more constraints. Number one, can I fly my drone when it's very cold? Let's say -10? Absolutely no, because simply the battery will fail. The last constraint is about the geometry. My question for you is, if we take random photos, just random photo, an image here and there, image here and there, the question for you is, can I build a 3D model from random photos taken to an object, or those photos or images must meet some sort of geometry constraint, which is explicitly, it's the overlap. Any help?
It should overlap.
It should overlap. Otherwise, remember, photogrammetry arises from the point that if a feature appears in two images, then I can find the 3D coordinates of this point. If a feature appears in one image, then there is no way for us to find the X, Y, Z of the point. So you can see here, since there are so many constraints, I guess by now you get the idea that we must do a good planning. And we already discussed the good planning. It means I have to pick the right date, the right day, the right time in the day. In addition to that, I need to come up with some geometry, constraint. Watch this, please. So I'm going to skip a few slides. You guys can enjoy reading. But here we go. I think I should get into this business right away. So here we go. This is a flight line. So my aircraft is simply flying this way. And here we go. Here is my aircraft. And when my aircraft was here, simply I took one image. And where is my image? Simply here is your image. From here to there, this is kind of your image. And if you're asking yourself how much my image covers on the ground, you can see simply this is how much your image covers on the ground, simply between this point to this point, okay? So this is how much will every image will cover on the ground, or at least the first image. And then what happens is your platform is in motion, so your aircraft is flying. So after some distance, which we call it here base of photography B, so which is simply the distance between your exposure station. So I took one image here, another image here, and this distance we call it B, which is the base of photography. Then we got another image here. So what is covered on the ground by the second image? Watch this, please. So what's covered on the ground by the second image is simply from here to there. Now I'm asking you, where is the overlap? You can see the overlap is simply labeled on my sketch as this number, huh? So anything that shows on the first image and the second image, this is called overlap area, okay? Now let me ask you a question. If I have any feature here, according to what you see on my screen, can I find XYZ for this point? Can I find XYZ for this point? It's not very difficult. All you have to do is, does this feature appear in two images or only one?
Just the one.
So if it's only one, then no 3D in this area. Now let's do the exercise one more time. If you only have the first and the second image, only two images, can I find the XYZ of this point?
No.
No, I guess you guys got the idea. So finally, I'm asking you, can I find an XYZ in this area, which we have an overlap? So which means my feature appears in this image like so. So it goes here and being projected on this image and also be projected on this image as well. So can we find a 3D information in the overlap area? I think the answer is yes. I keep repeating this all the time. It has to be overlapped. Now, when you think about the overlap, you can see the overlap is mentioned here on my sketch as a distance, okay? Now, I'm asking you, what if we take another image by the same base? So I travel another B here, and I repeat my third image. So if my third image comes, I guess when you look at it, you will see this area will be covered in two photos. I'm referring to this area here, from here to there. So if I get my third image, this area will also be covered by two photos. And it will go on and on and on and on and on and so on and so forth. Huh? Now I'm asking you, what do you think about the overlap percentage? So if we divide the overlap distance here by the coverage G, I'm asking you to see every point in my project in at least two photos. What is the minimum overlap? Is it 20%, 30%? How much?
50.
50%. And you can see simply if I'm able to maintain a 50% overlap between one image and the next image, looks like my entire area will be covered by at least two photos. And that's why you can see here, really my minimum overlap is 50%. But remember the following fact, that this 50%, we got it based on very, very simplistic assumptions. And what are the simplistic assumptions? That my ground is simply flat, my flying height is constant, and my sensor never tilted. And I'm asking you, do you think in reality, in the actual mission, those assumptions will happen all the time?
No.
It's not going to happen. You will never get a perfectly flat earth. You'll never maintain the flying height. You will never be able to maintain the verticality of your images. And that's why this 50% is the minimum. But in our design, we cannot survive with the minimum, because if only one thing happened, for example, if there is some air that pushed my aircraft down, or maybe tilted my sensor, or maybe the ground has some relief, in this case, you will get less than 50%. And I'm asking you, if we have some photos that they have less than 50% overlap, can I get a 3D model for the entire area, or there will be some areas missed? I cannot find the XYZ.
Some areas are missed.
Some areas as missed. That's why bottom line is, although 50% is the minimum, but we never go with the minimum because we need to have safety. And so we add between 10% to 25% for safety. And that's why in my design, finally, I set my overlap percentage to 60 to 75%. If you remember, in the last class, I gave you kind of very quick demo on Dex 4D Capture, which is an app that helps you to design the mission for drones. One of the parameters that you set during the flight mission design is the overlap percentage. The overlap percentage, okay? So again, bottom line is minimum 50. We have to add some extra for safety to ensure that every single point on my project will show in at least 2 photos by adding extra 10 to 25%. When you take 10 to 25%, add them to the minimum, which is 50, then your overlap should be 60 to 75%. Remember, the word overlap, it is between an image and the next image within the same flight line, okay? Now, guys, do you guys remember how do we cover the area? Let's say my project is here. This is a plan view for my project area. How do I cover the project area? Watch this. I go here and I fly along. I'm sorry, that's not what I meant. I simply wanted to use this one here, a polyline. So I go here. No, oh my God, no. So I go here and I say, you know what? Let's fly this way. Next is, after you finish your first flight line, you go this way and then go back and then you go back. So kind of a zigzag thing, huh? So you go on a parallel flight lines or parallel sweeps of the ground until you scan your entire area. If you guys remember, this was shown in several videos, okay? Now, I'm going to talk about an overlap, but it's not really between an image and the next image within the same flight line, okay? So this is something called side lab. So you can see I move from overlap to something called side lab. Now, I need you to understand the side lab and how it's different from overlap. So one more time, overlap is the covered area in two successive images within the same flight line, while side lab is the same covered area, but really between two different flight line. So probably I can turn this into a 3D. So this guy here, this is your flight line, and this is, so you went this way. When you came back, you went on a parallel flight line, you came this way. So what is the side lab? Side lab is simply this area here, which is between two adjacent flight line, not two successive images. Can I get some confirmation that you guys understand the difference between an overlap and side lab? Can I get some confirmation that you understand the difference between overlap and side lab?
Yeah.
Okay, so guys, side lab is simply it can be zero, it can be absolutely zero. And I know some of you will say, okay, oh wait. You keep saying overlap has to be minimum 50%. Why, when it comes to side lab, you can go to 0%? The thing is, we have already, if we're able to cover between this image, okay, so look at this, between this image here and the next image in the flight line, we should have a 50% overlap. But I'm talking about, this image in this flight line and this image in the next flight line. Absolutely. If this is zero, we're able to cover the entire area and build a 3D model. But the problem is, if I go exactly with zero, you have the same issue. Look at this, please. So here's my project area one more time. And I'm saying here, you know what? Here is my flight pattern. I'm going to go this way. I'll fly this way. And then I'll go this way and I'll fly this way. And with zero side lab. I'm asking you, what happens if the air pushed you sideways? For example, I went this way in real mission. I go this way, and then you get some wind where the wind pushed you this way. You know what's the problem? The problem is you will simply have one area on the ground, that doesn't show in any image. One area, one hole in the ground that doesn't show in any image. Okay, so as I said, let's say, for example, my images are like this. So, okay, I have one image, I have another image, and this is simply how much every image covered on the ground. And you can see we have overlap in between them. Okay, like so. My point, which I'm trying to make, is that if I maintain zero overlap, so you're just touching each other, maybe if I'm pushed by the air, maybe my image will become this way, and my next image will go this way. Okay, and you can see, let's look at this area here. This area here. Do you see this area here? I'm going to give it different color. I'm asking you, this area here, does it show in any image at all? Not only one, not even one. Does it show at all in your photo sequence?
No.
No, and that's why, although the minimum side lap theoretically can be zero, but again, we cannot use the zero in my design. We need to have some factor of safety. And that's why the minimum of factor of safety goes between 10 to 25%. And if you add this to zero, which is your minimum for side lab, then finally your side lab minimum, in your design should be 10 to 25%. All these parameters, we can set them on my app. You know what? 20 years ago, before the advancement of, of tablet and cell phone and all those things, we used to do manual calculations. Because look at this. Look at this, please. The amount of overlap, it controls the base of photography. So if I have a smaller overlap, I'm asking you, if I have a smaller overlap percentage, so this overlap is small, what happens to the B? Does it get bigger or smaller? When I have a small overlap percentage, the base of photography, does it get bigger or smaller?
Bigger.
It
Bigger.
gets bigger, huh? And that's why 20 years ago, people used to do that manually. So they say, okay, I want to have a 60% overlap. Okay. And because they have the flying height and they know the camera, they are able to find the overlap in distance. And then what happens is your G minus the overlap will give you the B, the base of photography. You guys are exactly right. When the overlap increased, then the base will get smaller. When the overlap decrease, the base gets larger. And remember, the base of photography controls, if you know the speed of your aircraft, then you can find the time interval because you have an aircraft traveling at speed and you want your camera to take an image every time, every specific interval. So anyway, I don't want to get into this business. I want to give you an idea of what happened 20 years ago. Based on these parameters, we estimate the base of photography. And if we know the base of photography, we can simply find the time interval between the photos. And then we go to our camera, we tell the camera, take photo every 1 second, every 2 seconds, every 3 seconds, okay? And remember, the more time, the larger the B, the less the overlap. The more time, the larger the base of photography, the less overlap. Okay, right now it's very neat. We don't have to do that. As soon as you enter the overlap and the side lab to your planning application or software, it will do all the calculation and simply set the location where you need to take one image. You can see here some of the danger. What happens if my flying height changes? You see what happens, huh? Look at this. If I'm designing on 50% exactly, and this happens, you are in trouble. Why is that? Because if my aircraft is pushed down by the air, then you see we lost the overlap here in this zone, okay? Between this point and this point, it will be simply shown in one image. Also, if you have a camera and the air simply tilt your sensor, you can see we also lose the overlap because of the tilt of the sensor. And that's why this is exactly the reason we need to add a factor of safety. Okay. Now here is, so this discussion is over. So this discussion is done. So now I have here another discussion, very, very interesting. This was part of my PhD when I did my PhD back at U of C about mobile mapping system. Okay, look at the name, mobile mapping system. And what the word mobile? The word mobile, it means it's moving, It is moving. And it means I'm trying to create a system that can do the mapping while in motion. This is the meaning of mobile mapping system. And we typically call it MMS. Okay, in literature, they call mobile mapping system as MMS. Now, this was a dream. What you see on my screen here was a dream for every surveyor. You know, surveying was done for years and years using a static technique. You guys remember first year surveying? How did you make a map for one area? I need to remind you. You pick points on the area called the traverse. You fix them on site. So this creates kind of a framework of coordinates. You measure this distance and angles, and you at the end of the exercise, you know their X, Y, Z. Then later on, after you adjust the traverse, you come back, occupy them one more time, and start measuring horizontal angle and vertical angle and slope distance to unknown point, a point that you want to find X, Y, Z. And then based on this measurement and the coordinates of the control point, then you should be able to find the XYZ. This is completely static, very slow, and very time consuming. Now, people ever since dreamt of the following. I need something that is moving on a speed while I can still create my map. And then back in around 1990s, huh? So this is kind of has a little bit of history. So around 1990s, when GPS started to be available, remember the idea of GPS was back from 1970s, but it was not really open for civilian before end of 90s, around the year of 2000. So we're able to buy our GPS receivers. Okay, before that, the system was not fully operational and it was only for military. Okay, around end of 1990s, now this system they start to appear because we have a GPS, we have digital cameras, and then finally we have something called INS. And I'll explain for you why every one of these components is very important for the using this system. Number one, the camera. Probably by now you figured out, huh? Camera, it means I can take photos around me, like let's say 360 degrees around me. And because I have photos, I can apply photogrammetry. Okay, because I have photos or images, I can apply photogrammetry. Now, GPS, obviously, the GPS, what it does, every time you take an image, the GPS will tag the image. Tag, it means add labels. Huh? It's okay, your location is, here is XYZ, where you take the image. So the purpose of the GPS is to locate the images in space. Now, this is not enough because we not only need the location, but also we need the orientation. So when we take one image, we want to say, okay, you know what? My camera was pointing to the east or pointing upward or downward. So how can I find the orientation of my camera? How can I do that? This is new. Probably you've never heard about this discussion ever before, okay? So there is a system called INS, Inertial Navigation System, not GPS, huh? So GPS is only for location, where it gives you the XYZ, while the INS is for orientation. So this system here, it simply finds for you where my camera was pointing in space. Is it pointing to the east or to the north or to the south or up or down? Gives you the full orientation of your camera. And I will give you a surprise, a very big surprise. Do you guys that every one of you guys, you have an INS and you never knew about it? In every cell phone, in every smartphone, it has INS. And simply, what is INS? INS, it's a combination of accelerometers, and gyroscopes. Probably you hear those names before. Anyone in the class heard about accelerometers and gyroscopes? Okay, so anyone in the class heard about acceleration? Don't be shy, because if you don't, then I think you shouldn't be in CBT. Anyone in the class heard about accelerometer or acceleration? Okay, I guess Matthew, huh? So acceleration is simply something that you guys probably heard in physics class, which represents the motion of the body. When something is in motion, there are three variables are changing, huh? The distance, the speed, and the acceleration, and they vary with time. So if you want to see the speed is the change of the distance over time. What is acceleration? It means this is the change of the velocity over time. And remember, the thing is, it goes by differentiation, huh? So it's a rate of a change. The rate of a change of distance over time is the speed, and the rate of the change of the speed over time is your acceleration. So accelerometers are little sensor that they can measure acceleration. And if we measure the acceleration and then we integrate, I'm not sure if you guys, anybody in the class learn about integration or differentiation somewhere in your math classes? Please show your hands. If you learn about integration or differentiation, thank you so much. You guys know, but you guys probably you forgot or maybe you're hiding. Integration is the opposite of differentiation. So if you have a sensor that measures the acceleration and you integrate the acceleration over the time, you're simply getting the speed. And if you integrate the speed over the time, you're getting a distance from where you started. This is how simply the INS works. I can tell you every cell phone has accelerometers and gyroscopes. Anyway, I'm going to leave it at this point. I give you a little bit of idea of what INS is. Bottom line is INS, it measures the orientation of any object in space. So it will tell you the camera, this camera was pointing to the east, and let's say it's, turn it up by 2 degrees, okay? It knows the orientation. With those information, like where's my camera and what is the orientation of the camera, I can find the XYZ based on image measurements. So all I do is click on the screen and I can find simply the XYZ. Now, some of you until now did not see the beauty or the power of this system. So here is the power of this system. Let's say you decided, or the city of Calgary or Alberta decided to create a map or update the map of the Canada Highway number 1 between Calgary and Banff. Calgary and Banff. Now, if you want to do this using traditional technique, like for example, GPS, oh my God, this will take forever, okay, using GPS or even total station. While if you're using mobile mapping system, all you have to do is the following. You need to have this van, which is simply not easy because this van is very expensive. And I'll try to tell you kind of a round figure of how this van, how much the system will cost. But what you have to do is you need to get the van and then simply hire a driver. The driver has zero surveying experience, zero, knows nothing about surveying. All he or she knows is that they are able to jump in the car and then drive. Start the system, and the system first, before you start, it will communicate with the camera, make sure the camera is okay, the GPS has good signal. Fine, it will give a green light, okay, drive me. And then you drive from here to Banff. How long? Any thoughts of how long to go from Calgary to Banff? How long? Oh my God.
Over an hour.
1 hour, 30 minutes maximum, I guess, right?
Yeah.
But guess what? As soon as you arrive in Banff, the system has collected all the data that you need to use to create a map for this segment of the road. So in 1 hour, 30 minutes, because we drive at the road speed, the system is fast enough to keep taking photos along the road. You don't have to stop. You're in continuous motion. The system will take all these data, and then finally, once you arrive in Banff, you can simply use the data to create your map. It takes more time in the office, so I'm going to show you later on what's being done in the office. But guess what? Your field time was cut to 1 hour, 30 minutes for surveying more than 100 kilometers of the road, because you're moving on 100 kilometers per hour mainly, okay? And so more time will be in the office, but that's amazing because you don't have to build a traverse or maybe nothing. Just using the system is enough. No need to establish a traverse. No need to spend hours and hours and hours. No need to spend to hire 100 surveyors, okay? So now with this system, you should be able to survey any range away from the camera within 30 to 50 meter. For sure, if you want to survey points which is way, way far from the road, then that doesn't work. Huh? So the feature should be on the road or very close to the road. Now, let's see or take a look at those images. Huh? So I used to teach this from PowerPoint where you can see all the photos, but I'm using this right now from PDF. So that's why I cannot do animation. Okay. But anyone recognize where this photo was taken? I'll zoom in, huh? I'll zoom in and check you guys. If you live in Calgary here for a few years, you should know where this photo, huh? You can guess.
Downtown.
Downtown, 9th Ave. The train is on your right side here. That's 9th Ave. Thank you so much. And again, this is an example of the picture taken by the system. And I'm not sure if you're able to zoom in here. If I zoom in here, this is very poor resolution. But if you have a good, I mean, the original one, you should see able to see here that for every image, the location of the image and the orientation of the image was known and measured and tagged with the image. So it means I know I was heading east. I guess we were heading east, and maybe I have maybe tilt angle, maybe 2 or 3 degrees down. So you know what? This is what the system does. It captures the image, but the image are geotagged. It means every image of known location because we have GPS and of known orientation because we have INS. Now what's next? Watch the beauty. So the beauty is you spend 1 hour, 30 minutes on site acquiring your data. Then once you finish, then you simply have to do some processing like on the GPS data. And then once processing is done, you can upload the data to a server. And I think server, I'm not sure if you guys know what does mean server. It means there are so many terminals connected to the same data and they do parallel processing. So we could hire, for example, 100 students in China and 100 students in Egypt and 100 students in India, and all of them, they are connected themselves to the data on the server here in Calgary. Okay? And then finally, we do the feature extraction so we can do our mapping. Okay? Now, watch this, please. So, for example, here is an example on how we do the mapping. I think this is also in Calgary here, but it's not very common, like very clear where it is. But this set was in Calgary. So very simple. Once you see a feature, and this feature here is our fire hydrant, and you want to find the XYZ of the fire hydrant. So all you have to do is, as I said, the system has more than one image, sorry, more than one camera. Like I remember the one I used has 6 cameras, and the 6 cameras are pointing in different direction on the horizon. So maybe 2 pointing forward and 2 pointing to the side and then 2 pointing backward. And what does it mean? It means I will see my feature in more than one image. So all you have to do is click. So click here, watch this. So click here in one image and then click here in another image. And you guys know, if I'm able to measure my point in 2 images, what can I get? I can find the XYZ, the XYZ. Okay. By the way, I think the areas here, it's in the northwest of Calgary. This is Country Hills. You can see a map on the left, Country Hills, and this Nose Hill, huh? Nose Hill Drive Northwest, if you're familiar with this area. Okay, now, for example, I am driving my car on the street. I capture these images. And again, if you zoom in here, do you see what's here? It tells you the location. It tells you the date it was taken. Now, when you look at this image, you can see there is a bridge. Huh? Can we measure the clearance of the bridge? Can we do mapping of the bridge? Because simply the bridge will be not more than few points. Huh? So we measure a point here and measure a point here, and these points will simply create for you a map, the bridge. Okay. Now look at the beauty. Okay. Now there is even while you're mapping, you can even attach to the XYZ the type of the feature. It is something that we struggle in total station. Watch this. So let's say on the software, I see 3 images, and in 3 images, I can see school zone sign. So I'm going to click here. So I'm going to click here on first image, and then click here on the second image, and maybe I can click here on the third image. And what do I get? I get XYZ. You can see here, I get XYZ of the point. But not only XYZ because it's an image, so I can see that this was a school zone. I can click here on the library and I can attach my symbol to my point. How this is connected to the surveying using total station? Remember, do you remember descriptor or description, point description?
Yes.
I'm asking you, is there any way to make a mistake here while using photogrammetry? Is there a way to, for example, to classify this school zone as a stop sign or a tree? Tell me, please. Can you do this mistake, or it's obvious because you have a photo, so it tells you what was my feature. In total station, we measure distance and angles, and we attach a description for the point, but I can make a mistake. But if you use photogrammetry, you can find the XYZ and click here on the library and say, okay, you know what? Here is a school zone. Okay, now let me ask you what this system is good for. So now you've seen the system, and you know some ideas about the system. Here is some application for the system. Okay, number one is pavement visual inspection. And you guys, this is something City of Calgary will do it, I think, on a yearly basis. You see all the time in summer where they have the road construction season, huh? All the time they have road closure because simply our weather is very aggressive. -40 in winter, +30 in summer, and this causes cracks and problem with our roads. So part of the things we do visual inspection. But if you have this system, do you really have to walk on the road, or you just walk on the roads and then when you go to the office, you can do the visual inspection through the photos? You can even measure the length of the crack. You can measure the width of the crack. And if the crack is too big, then you can mark this for the next maintenance. Next is we have road sign inventory and road utility inventory. And what does it mean? As you go on the road in your photos, you can see all the signs, so you can count them, know where they are, you can know where are the bus stations and so on. You can create an inventory for the signs, road signs. You can do the same thing on the manholes. Anything that can be seen in the image, you can simply capture whether you get XYZ or at least count. Okay. Now, also we have a common problem, which is road clearance. So sometimes we want to see the road clearance. We want to see how much under bridges. This is something which is difficult to do using manual measurement. Okay. Manual measurement, it takes more time, and probably you have to stop the road. You have to stop the traffic. If you are using this mobile mapping system, you don't have to stop the traffic. You just drive your car under the bridge, and then you can find the clearance under the bridge without having to stop the road. And then finally, which is something that we discuss in our class here, it's about mapping. Okay, so basically with the mobile mapping system, you can simply have a complete map of your road, including all the geometric information like the horizontal and vertical curves and sign and line of sight, and you can do lots of analysis there. Okay, so I would say this system really works very well. The only downside is the price. Okay, the only downside is the price. Okay, the price includes a platform for sure. So you need a platform. You need GPS, which is not expensive. You need some fast camera, which is also not very expensive. Inside the van, there must be a machine. And I'm saying machine, it means a computer. Huh? I'm asking you, this computer should be fast, or it can be a slow computer. Can anybody tell me it has to be fast? It's a must, huh?
Yes.
Remember, you're driving at 100 kilometer per hour, 100 kilometer per hour, and you you wanna capture a set of photos, not only one, huh? Let's say you have 6 cameras, so you wanna capture an array of photos every few seconds or every fraction of a second, for example. This requires a very fast computer to be able to capture, like let's say 20 mega every fraction of second. Needs a very fast computer. Okay. Really, what is very expensive is that INS. Okay. And some of you will say, oh, wait. You just mentioned that every one of our cell phone has INS. And I buy my cell phone, let's say $500 or even $1,000. The thing is, yes, your cell phone has INS, but it's kind of a cheap INS. So the accelerometer and gyroscopes, they are very cheap, okay? They are good for the purpose for the phone, but this one INS here, which still has the same accelerometers and gyroscope, but those are very expensive because they are very sensitive. So they can sense very little motion of the platform. So we can get a millimeter level of accuracy, okay? So this one, I can give you a number. This guy here, about 100,000 US dollar. The price of the INS is 100,000 US dollar. But guess what? It's not only about money. Let's say if you're rich, let's say you have 130,000 Canadian dollar and you wanna apply and buy your INS. I'm gonna tell you something, you will never believe it. You can't. Okay? You can't, because this is something protected. If you wanna buy an INS, you must go through US security, because those are very, very sensitive, technology, because they are used on missiles, because they are used to guide missiles. Because GPS is not reliable, so there's something beyond our discussion. But GPS is not reliable, because if USA decided to shut the GPS signal, they can do that, and they have done it already. I think maybe a couple of times. One back in 2001, I guess, 2001, like September 11, they decided that this is a national security, and they shut down the signal of GPS. So remember, the GPS needs a signal. It doesn't work by itself. So if you buy a GPS and there is no signal, then it's just like a piece of metal, It doesn't work anything. A GPS receiver needs a signal. The signal is controlled by the countries that they operating the system. While INS, this guy here, doesn't require any signal. The signal is your acceleration and your velocity. And this something doesn't require any external signal. And that's why if you want to buy INS, then you need to apply for US security. I think if I remember correctly, it takes about more than 1 year, and to get some clearance, and then you can buy. Do you want to make sure that you are not belong to terror group or something like that? Okay, and then now you can buy it. At UFC, I remember there was only 2 individuals who went through the US clearance, and they are able to sign off the INS. UFC, by the way, owns one of those INS devices. I'm hoping that this was interesting and something to be proud. Something to be proud. This system primarily evolved from Calgary. So Calgary is the mother of this system. Like back in 1990s, there was only two systems worldwide. One here at UFC, and the other one is in Ohio State University. Only two worldwide. In 2021, I think there is more than 400 companies and systems available in the market. But back in 2000, there is only two systems available worldwide. One of them was in Calgary, and the other one is on Ohio State University in USA. Any question regarding what I discussed so far? Because we need to take a break, and after the break, we will discuss satellite photogrammetry.
So does INS still give you the XYZ then?
Good question. Okay, so the INS finds for you all the states, like find for you the X, Y, Z, and the 3 angles in space, like the orientation about the 3 different axes. However, INS has some noise, and the amount of noise is function of the quality of the sensor. So when I measure acceleration, it comes with a noise. And if I integrate, the noise will accumulate, because integration is summation. Integration is summation. So if you integrate over the time, simply the noise will accumulate in the error position, and error in the orientation. So what happens here, the GPS and the INS, they are used as augmentation. They augment each other. And what does it mean? It means if the GPS is available, it will augment the INS. So it will tell the INS you are here. So, and this will be able to kind of correct the errors. If the GPS is not available, and this happens if you pass under a bridge, what happened to the GPS signal? You don't see the sky. your signal is occluded by the by the slab of the bridge. It means that you don't see the GPS. Whenever you don't see the GPS, so now we have a outage. Let's call it outage. In this case, your INS will augment the GPS. I'm not sure if you understand what I said. If you don't understand, never mind. It's okay. Okay, it's not connected to our course. But the GPS and INS, they augment each other.
Yeah, for the most part, I think I followed.
Thank you. Any other question, guys? So if you okay, Kitan, go ahead.
Yeah. Are there any types of INS, or it's just one kind of that's costliest one?
The most costly one, but you know what? Like there are some other hardware, like you have something called frame grabber. So again, you guys are not expert. I'm not expert, but the system has more component. So inside here, there's something called frame grabber, and the frame grabber it simply communicate with the camera and grabs very quickly the images and store them into the computer. So there are some other electronics there here, which I'm not expert. I'm just telling you. So the whole price here, probably including the software, about $750,000. So including the INS, the camera, GPS, the van, and the software. Remember, the software that logs all the data is also a property of the company, or UFC. So if you want to buy this system right now, I think it will cost you between $500,000 and then $750,000. So the initial cost is very high, but it's very productive. Any other questions for now? I'm happy that I can see at least some of you guys are interested to know about these systems. Okay. By the way, so you know, some of you may think by now that this is similar to Google Earth. I know some of you already think about this one as Google Earth. Any one of you guys seen Google Earth cars on the street? Have you seen one of those? Show your hands, please. Show your hand. I myself have seen Google car that create a street view. Have you used Street View? Did you use Street View before? Google Street View? No? Amazing. Amazing. Do you want me to show Google Street View, or you have done? I'm pretty sure you guys use it. It's impossible. Yes, you see, you guys are hiding. You have used Street View. You just grab the little guy on the bottom right corner of a street map, like a Google map, and it will show you around. In most cases, in North America, I think we have surveyed everything almost. Okay. Just grab the little guy in yellow on the bottom right corner of your Google map, and it will give you a street view. Okay. But I want to say something before the break. This system is not Google Street View. The system, it is for mapping. Google Street View is for fun. They have something called iFish lens, which this lens has 360 degrees field of view, and this has lots of distortion and cannot be used for accurate mapping. This system here, I have done some testing back in 2009, and you can find a map with accuracy better than 5 centimeter, which is equivalent to simply the GPS accuracy, plus or minus 5 centimeter. So that's amazing, given the speed of the system. Any other question before we break? Okay, so it's 12:52. We'll take 10 minutes a break. We'll come back here at 1:03 sharp. Thank you.